Our sun is a dynamic and powerful star, constantly in motion and full of energy. It constantly releases energy, including bursts of intense radiation known as solar flares. These flares are like sudden explosions on the sun's surface, releasing a tremendous amount of energy in a very short time. These flares originate from sunspots, which are cooler regions on the sun's surface associated with strong magnetic fields. Sunspots appear darker because they are cooler than the surrounding areas, but they are still incredibly hot and active. Imagine twisting rubber bands until they snap. That's the sudden release of energy we see in a solar flare. The magnetic fields in sunspots can become twisted and tangled, and when they suddenly realign, they release energy in the form of a solar flare. Solar flares emit a wide range of radiation, including X-rays and ultraviolet light. This radiation can travel through space and reach Earth, affecting our planet in various ways. This radiation travels at the speed of light, reaching Earth in just over 8 minutes. Despite the vast distance, the effects of solar flares can be felt almost instantaneously. While our atmosphere protects us from the most harmful effects, solar flares can still impact our technology and way of life. For instance, they can disrupt satellite communications, GPS signals, and even power grids. Understanding solar flares is crucial for comprehending the dynamic relationship between the sun and Earth. The sun's activity can influence our planet's environment and technological systems. As we rely more heavily on technology, the potential impact of these solar events becomes increasingly significant. By studying solar flares, scientists can better predict and mitigate their effects, helping to protect our technology and way of life. Fortunately, Earth is protected by a magnetic field, a shield against the sun's powerful emissions. This magnetic field is crucial for life on our planet, acting as a barrier that prevents harmful solar radiation from reaching the surface. This field, generated by our planet's core, acts like a giant bar magnet, deflecting most of the charged particles from solar flares. The core's movement creates electric currents, which in turn produce the magnetic field. This dynamic process is known as the geodynamo. Imagine holding a magnet near iron filings. The filings align with the magnetic field lines. This simple demonstration helps us visualize how Earth's magnetic field operates on a much larger scale. Similarly, Earth's magnetic field guides the solar wind, a stream of charged particles constantly flowing from the sun around our planet. This deflection is vital in protecting our atmosphere from being stripped away by these solar winds. However, intense solar flares can cause a sudden increase in the solar wind, creating a geomagnetic storm. These storms can compress the magnetic field, allowing some particles to penetrate deeper into the magnetosphere. Think of it like a wave crashing against a seawall. The magnetic field absorbs the initial impact, but the energy can still disrupt our technological systems. This can lead to issues such as satellite malfunctions, power grid failures, and communication disruptions. Understanding the interaction between solar storms and Earth's magnetic field is essential for assessing the potential risks to our planet and developing strategies for mitigation. Scientists continuously monitor solar activity and study the magnetosphere to predict and prepare for these geomagnetic events. By doing so, we can better protect our technology and infrastructure from the sun's powerful outbursts. One of the most immediate impacts of solar flares is on communication systems. Radio waves, used for everything from broadcasting to navigation, can be disrupted by the increased ionization in Earth's upper atmosphere caused by solar flares. Imagine static on a radio during a thunderstorm. That's the kind of interference solar flares can cause. High-frequency radio communication, often used in aviation and emergency services, is particularly vulnerable. Solar flares can cause blackouts in these frequencies, hindering critical communication channels. Imagine pilots losing contact with air traffic control during a solar storm. The potential for chaos is evident. As our reliance on seamless communication grows, so too does the importance of understanding and mitigating the risks posed by solar flares to these systems. Section 4. Satellites in Peril. The vulnerability of orbiting technology. Satellites orbiting high above Earth are particularly vulnerable to the effects of solar flares. The intense radiation can damage solar panels, disrupt onboard electronics, and even drag satellites out of their orbits. Imagine a satellite losing power or experiencing a computer malfunction due to a solar storm. The consequences could be significant. GPS navigation, Weather forecasting and communication networks all rely heavily on satellites. A major solar flare event could disrupt these services, impacting global economies and everyday life. Imagine losing access to GPS navigation or experiencing widespread internet outages. The world would feel the effects immediately. Protecting our satellite infrastructure from the damaging effects of solar flares is crucial for maintaining the technological advancements of the 21st century. Section 5. The power grid's fragile balance, solar storms and blackouts. In this section, we delve into the intricate relationship between solar storms and the stability of our power grids. While Earth's magnetic field protects us from the most harmful effects of solar flares, intense geomagnetic storms can induce electric currents in power grids. These storms are caused by solar flares and coronal mass ejections from the sun, which send charged particles hurtling towards Earth. These currents, flowing through long conductors like power lines, can overload transformers and cause widespread blackouts. The induced currents can be so powerful that they disrupt the normal flow of electricity, leading to catastrophic failures in the grid. Imagine a surge of electricity overloading a circuit breaker. On a larger scale, this is what can happen to power grids during a solar storm. The sudden influx of energy can cause transformers to overheat, circuit breakers to trip, and entire sections of the grid to shut down. The 1989 Quebec blackout, which left millions without power for hours, was caused by a geomagnetic storm. This event serves as a stark reminder of the potential consequences of solar activity on our modern infrastructure. This event highlighted the vulnerability of power grids to solar activity. Experts have since been working on understanding and mitigating these risks, but the challenge remains significant. Imagine a similar event occurring today. With our increased reliance on electricity, the economic and societal impacts would be enormous. From communication networks to transportation systems, nearly every aspect of our daily lives depends on a stable power supply. Strengthening power grids and developing strategies for managing the flow of electricity during geomagnetic storms are essential for ensuring the reliability of our energy infrastructure. Engineers and scientists are continuously researching ways to make our power grids more resilient, including the development of advanced monitoring systems and protective technologies. These efforts include installing sensors that can detect geomagnetic disturbances in real time, allowing for quick responses to potential threats. Additionally, protective devices such as surge protectors and advanced circuit breakers are being developed to safeguard critical components of the grid. By investing in these technologies and strategies, we can better prepare for the inevitable solar storms and ensure that our power grids remain robust and reliable, keeping our cities bright and our lives uninterrupted.